All right, so video going over the basics, essentially, of heat transfer. Okay, so the purpose of this is to kind of understand uh, how energy is transferred in the there we go, major ways commonly taught. Okay, and you might say, okay, that sounds kind of reductive, but it's useful. Like I think it's a good way to think about heat or energy in general is how it interacts with matter. Right? We often think of energy and matter as different. As you go up the ladder of science, you learn they're actually very much the same. It's just like how they work together. I don't know. They like go together very well. They make one thing. The energy matter duality. They're interchangeable. Okay, but when you're first learning about them, we often think about it as they're separate. Okay, we think of energy can travel, can transfer, and it can use matter to do that. Okay, so that's kind of what we're getting at here today. So I have here in front of us, it's a little simulator from PhET. I like these things a lot. Very nice way to visualize hard things that, very difficult to picture this without you kind of having something in front of you, right? And this is just a way to show you what I'll be getting at. Okay, so we have these little molecules, little atoms. In this case of neon, it really doesn't matter what I pick. Okay, neon though, right now in the solid phase. How do you know they're solid? Hopefully you're saying, well, they're not moving past each other. These molecules, yes, they're vibrating, they're shaking in place, but they're not flowing. If I give it a little bit of heat, right, give it a little bit of energy, they vibrate a little bit faster. Right, we can see that the temperature's gone up. By the way, this temperature is insanely cold. 19 Kelvin is, I mean, in Fahrenheit, that's like negative 400 or something obscene. Okay, if I put it in Celsius, right, negative 254. Pretty cold. Okay, neon freezes at a very low temperature. Okay, give it a little more heat, right, and we begin to get to a part where you can see it basically melting, right? That's what you're seeing here is the atoms beginning to flow around each other, right? They still want to hang out near each other. You can see the occasional one or two that are going off, all right? We're going to ignore what's called vapor pressure for this. That's a little bit too complicated for this. Basically, these atoms are in the liquid phase. They can flow around each other, okay? I want you to picture, this simulator doesn't do it perfectly, but I want you to picture that these molecules, right, are moving around. They have velocity. They have mass, which means they have momentum, right? Momentum is mass times velocity. And as they go around, they sometimes hit each other. They transfer energy, just like imagine like two bumper cars, okay? These molecules also hit their surroundings, right? You can see this pot they're in, right? They are bouncing off the walls. And when they hit the wall, they're transferring some of that energy into the wall. How does that energy get transferred? Basically is heat. Okay, I say basically, it gets a little more complicated. If you say, I don't believe you, right, if we increase the pressure in here, okay, the premise here is that I'm trying to compress these molecules, which means now when they hit the walls, there's more collisions, there's more interactions with the wall, which means basically we're taking that kinetic energy of motion and converting it into thermal energy. Okay? If you compress something, you're basically, think of it, if it helps you understand it, as like the friction between these molecules is increasing. That's how you could kind of visualize this. Okay, and if I, of course, decrease the pressure, the temperature goes down. Okay, this is one of the reasons why, if you've ever had like a can of like air duster, stuff you used to like clean like a keyboard of a computer, I guess it's really only, I guess that's their major use, right? It sprays air. Okay, how does it work? It's compressed liquid. It's been compressed. It's in liquid phase, and when you press the trigger, it lets air escape quickly. Okay, when you hold the trigger, you might feel the can gets cold. Okay, the can gets cold because energy is used to cause it to evaporate. Okay, that's also how an air conditioner works, incidentally. Maybe you're saying right now, I don't know where he's going with this. Just trying to have you think about these molecules. Okay, notice that by doing this, right, by giving the volume back, the temperature is still the same in this case, and that allowed the neon to turn to a gas. Okay, and this is a really good way to picture this. These molecules now are very obviously moving past each other, bumping into each other. If you put something in there, so let's say I put a piece of hot metal, the hot metal, okay, it can't flow, right? The molecules of iron, let's say, cannot move past each other. They're just sitting there vibrating very, very, very quickly. A neon atom could come by, hit that hot metal, and bounce off. In the very short amount of time that it touches the hot shaking metal, it transfers heat. And now this thing is shaking faster and it can bounce away and go faster. That's how heat transfers. Okay? That transfer would be a good example of what conduction is, right? Conduction requires two things to be touching. Okay? So if you go back then to a more general picture and imagine like a steak being put on a stove, right? You hold the steak above the pan, I should say pan, right? Don't put it right on the stove, that would be silly. Take the steak, hold it above the pan. It'll cook, but it'll take a ton of time, right? As a little kid, you may put your hand above the stove, you feel heat. You feel the heat coming off the stove. You get closer, it gets hotter, closer, it gets hotter. If you touch the stove for even a split second, it instantly burns you. The steak, as soon as you touch the pan, it sizzles. It instantly starts getting cooked, okay? Because the transfer of energy can be faster during what's called conduction, okay? The molecules can touch. Now, it's not just the molecules or the atoms of iron here shaking very quickly, right? They're shaking here. The steak touches it. The molecules of steak is a mixture. We're just going to say molecules of steak. They start shaking fast. And what do? They shake the ones above them. And they shake the ones above them. Okay? What's happening each layer, though? There's less energy going up because the energy is being used to change the steak, to cook it. Okay? Chemical reactions are occurring. That's what cooking is. Okay? So each layer is getting less energy, less energy. They're shaking less and less. Eventually, there's basically no heat. Okay? So even though the bottom of your steak is cooking, the top of your steak, you could be cooking it for 10 minutes. Looks like it's never been touched because the heat can't travel through all that. Or rather, it's taking a very long amount of time. So you flip the steak over, and now that top layer of steak that wasn't cooked is now on the bottom. And it can touch those molecules of hot iron and, again, begin the process. This is why you flip things when you cook them. Okay? That's conduction. Conduction's very fast. It's the fastest of the three ways to transfer heat. Okay, because the molecules can touch. That's the key. All right. So then go to the second one, which is called convection. Convection is different because instead of the two items touching, so steak, pan, conduction is touching. The next one will be convection. And what's in between my pan, that's hot, and the cold steak? There's air. Okay. The air is what we call a fluid. Now, when I say fluid, people often think, oh, like liquids. Yeah, they're fluids, but so is a gas. Okay, fluid means what? If you look at the screen, they're flowing, those atoms are moving around. That is a fluid. Okay, so it doesn't matter if it's water, right? Like this, right? That liquid water, they can move around, can flow. Get it hot enough, right? Get this water to a high enough temperature, okay, and it will turn into a gas. Okay, oops, that's not what I meant to click. There we go. Okay, a gas is also a fluid. This would be steam. Steam is a fluid, not just because it feels wet, right? It's a flow of molecules. Those molecules, or atoms, in this case it's molecules, can help transfer heat. They're like a messenger. So imagine the hot pan is hot, shaking atoms, right? The steak is cold, atoms that are, moving a little bit. The air that is hitting the pan, right? We're on Earth, there's air that hits the pan, they get energy, they shoot up, and where do they hit? The steak. And they slowly begin to transfer the energy, okay? You can cook very quickly with convection, okay? Like it's not like it has to be slow. Generally speaking, though, it's going to be faster to cook with conduction. You may have heard of a convection oven. When you guys have heard of air fryers, that's what an air fryer is. It's just a convection oven. How do they work? Well, it heats up the air just like an oven, but it has a fan. And what does the fan do? It moves the air around the object, whatever's being cooked, the fries, whatever. And those hot air molecules, again, they can transfer more heat into the French fries, into the steak, whatever you're cooking, okay, compared to just heating hot air. Okay, take that hot air, move it around, you can cook the item faster, okay? But again, convection requires a fluid, okay? Could be water, could be steam, could be olive oil. It could be like a refrigerator. It uses what's called refrigerant, which is a liquid that is used to cool the coils, what's called the heat exchanger. That is a fluid. It's moving around through pipes. Okay. In your house, you have a furnace. The furnace heats up the air, hot air, and then what do? We blow air over the heat exchanger, which is basically a radiator. That cold air picks up heat, right, because it's touching the hot metal. That hot air now moves, and you move it through pipes. Well, they're called air ducts, right, through ducts of your house. That's convection. Okay, that hot air comes out of the registers, which is the name of the little register is the fancy word for the thing coming out of the floor that lets the hot air out. Okay, and that's how you heat your house. Okay, old-fashioned houses, some of them, use steam radiators. Okay, this is a good time to talk about this, right? A steam radiator, if you look at it, looks like this. You might have one in your house. You might say, hey, I got one right here. Okay, I don't have one here, but you might look at it and say, oh, okay. If you look at the design of a steam radiator, it has what looks like pipes that go like in a circuitous pattern, if that makes sense. Okay, the steam comes in from one end. So in this case, they're showing it over here. Okay, and the hot steam is traveling. Oh, this is a cool little GIF that it gave us. The hot steam is traveling through the pipes. And we want it to take time. We actually want the steam to take as much time as possible, because what is the steam doing to the metal? It's heating up. Notice the design. You have air in between each pipe. Air can travel through those and heat the air. How could you make this better? You could put like a fan behind it, right? Blow air through it. That would speed up the heat dissipation. Okay. Point is, this would be convection. Okay. Hopefully it's making sense. That leaves the last kind of energy transfer, which is called radiation. Now, when we say radiation, you might think, oh no, like X-rays, gamma rays, right? Things that can give you cancer. Those are examples of ionizing radiation, okay, which is a fancy way of saying they can basically destroy your DNA, cause problems with your DNA. DNA, the set of instructions that cells have, if you damage it, it can cause cancer. Okay, cancer, in case you're wondering, is basically cells that go radical. They say we're going to make copies of ourselves and not stop. Your cells have to make copies of themselves, but they have to stop at a certain point. If they don't, they're supposed to destroy themselves, a process called apoptosis, right? If the DNA gets damaged, they might lose that instruction, and they just keep making copies. They just don't stop, and that's what cancer is, okay? So in case you're wondering. Back to this, though. Radiation does not have to be that, though, okay? We have what's called electromagnetic radiation, okay? So if you think about energy, gamma rays, the ones that you're thinking of here, think about giving cancer, that can kill you, like in minutes, okay? If you get radiation poisoning, that can kill you in a couple days, okay? Forget about cancer. That's not your worry at that point. It's just your body getting destroyed, basically, because of radiation. That's very high energy radiation, okay? As you go decrease in energy, you get to safer kinds of radiation. The fact that you can see this video is because of radiation. I don't just mean like, oh, nuclear power. I mean you're seeing me, okay, because there's visible light coming off your computer screen. That visible light is radiation. Is it dangerous? No, perfectly safe, right? Not going to give me cancer. That is think of it as medium amount of energy. Okay, right past visible light is ultraviolet, and that is dangerous, right? That is the kind of radiation from the sun, for example, that can give you cancer. Okay, skin cancer specifically. Okay, UV radiation, we can't see it, right? It's higher energy than visible light. It's called ultraviolet because it would be, if you could see it, it would be kind of like very light purple. Okay. It's close to violet color is the idea. On the other side of visible color, right, think about the rainbow, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Red is the low energy light, okay? And right next to red is what's called infrared. That is radiation. Our bodies right now are making that radiation. You are making it, okay? You can't see it because our eyes can't see infrared. Okay, but if I were to turn off all the lights in here, right, you'd say he's gone. It's all pitch black. If the camera that I'm looking at could see in the infrared, right, if we look at that, I'll kind of show you what that would look like. Infrared camera, okay, You've probably seen these things before. You're probably like, oh yeah, like a FLIR camera, right? FLIR, right? IR, infrared. And you can see here it's looking at heat. Okay, so yes, I can't see this, right? I can't see the heat coming out of my house, but this is what infrared would look like, and our bodies would look like that too. Okay, so there's radiation being emitted. All right, now we live on Earth. There's air. The air takes the heat from our bodies and helps move it away. This is why if you blow on your hand, it feels cold. The air you're blowing is actually warmer than the air, right? Unless you're in like the desert, right? In that your lungs have heated up the air. The air you're blowing out is probably in like the high 80s, low 90s minimum, Fahrenheit, of course, which means it should feel warm, but it feels cold because you're moving air away. You're taking heat from your body and pushing it away. Okay? Hope that makes sense. The premise, of course, is that that's because there's air. There's convection. If I took away all the air, okay, you would feel warmer pretty much instantly because the air that is helping remove heat from your body, right, is no longer there. And the only way to remove heat now would be radiation. Okay, your body emitting these wavelengths of infrared radiation. And it takes a lot more time for it to emit radiation than for convection. Convection basically speeds it up. It helps the process along. Okay, radiation is if there's no air. In space, if I were to put you in outer space right now, you would die for many reasons. It's not. You might say, "Oh, you die because it's cold." That's the last reason you would die. Okay, the first reason is no pressure. Your eyeballs would explode. Your blood would boil. That'd be bad. Okay, the other reason you'd hypoxia, the lack of oxygen. You need oxygen, right? You can only go, I think it's like 3 minutes before you pass out maximum, and then after that it's like 15 minutes before your brain dies. Okay, and even then 15 actually that sounds kind of high. But anyway, don't find out the hard way, right? Point is that the cold would be the last reason to kill you because in space, even though it's super, super, super cold, right? We're talking near absolute zero in many parts of space. There's no air to pull the heat off of you. There's no convection, which means the only way your body is losing heat is from radiation. It takes a lot of time, which means it would probably take 15, 20, 30 minutes for you to get hypothermia in space, even though the temperature is insanely cold, way colder than anywhere on Earth, okay? But you would die faster from hypothermia if you were in Antarctica in the wintertime than you would in space, okay? You say there's no way. It's a lot warmer in Antarctica. I know, but there's a lot of wind, right? Antarctica gets very windy. If you go outside during an Antarctic storm, and if it's, say, August, and you might say, wait, August, that's summertime. Remember, Antarctica's in the southern hemisphere, so their seasons are opposite of the northern hemisphere. That would be right in the middle of their winter. It would be, we're talking temperatures negative 90 with a wind chill probably above like negative 150, okay? That would kill you faster than being in space, okay? Now, if you were to grab a metal bar of the space station, let's say you're at the International Space Station and you were to grab a metal bar with your bare hand, then you might die a lot quicker because all of a sudden the heat can travel to that metal bar and pull heat out of you very quickly. Okay? So I'm talking about just being in space, not touching anything, right? If you touch something, then all bets are off, okay? Anyway, so hopefully this makes sense. Conduction, convection, and radiation. And the name of the game, I've had this up this whole time showing you this, is it's these atoms, these molecules helping to move the energy. If you don't have them, if you don't have mass, it's got to be radiation. And if you look at that, let me just show you, not antenna, that's not what I want. No. Just to kind of put the cherry on top here, right? If you look at these waves, this is what they look like. Okay, you can't literally see them, right? But the notion is this energy that's traveling along a wave. And these waves can travel with no matter, travel in space. There's radio waves right now being emitted from the planet Jupiter, seriously, that are hitting us. Okay, perfectly safe, no danger. You can actually turn your radio on and listen to Jupiter. It's kind of cool. It doesn't sound like anything, by the way. It just sounds like static. But the premise is that Jupiter is emitting radio waves. Jupiter is also emitting a lot of other kinds of radiation. But it's kind of cool to think about, right? That it's emitting radio waves that you could tune into right now. If you ask me what radio station it is, I don't know if your car can. I think you need a special set, basically, where you can listen to more ranges of radio waves. If you look at this little picture here, let's do this, right? Yeah, there we go. Perfect. Right. Looking at types of radiation, right? Radio waves are very big waves. 10 to the 3 meters. That means they're a kilometer long. That's a very, very big wave. Okay. You can see then when we get to gamma rays, those are dangerous. These are dangerous territory. This is like get killed in a couple of minutes if you're near it. Okay. X-rays we all know about. X-rays are dangerous. You can have some exposure, right? You don't get 50 X-rays a day. That would be very dangerous, right? Ultraviolet, of course, visible, what we can see. Infrared, right? Microwaves are not that dangerous, FYI. I'm not saying put your head in the microwave, but it's not because of radiation that it kills you, right? And then, of course, radio waves. Okay, at the end. So hope this all made sense. And in space right now, these are all traveling through there. From the sun, we got all of these. A little bit of gamma rays. I don't think it's that much, though. Okay, you can see here the temperature where stars basically what's called the peak emission, aka it doesn't just stop there, but think of it as that's most of the waves. So like our sun, for example, is a lot of a lot of visible and a lot of ultraviolet, right? You get to blue stars like Rigel, for example, then you might be getting a lot of X-rays and whatnot. Pretty dangerous stuff. So anyway, hope this video was helpful and hope it made sense to you. Have a good rest of your day.